can be a tag, like associated, for example, your data is collected from AP01, or it could be more like a GPS type of measurements, having your data based on longitude, latitude. The temporal dimension is also important, but usually the temporal dimension is a numerical value. You just, as long as you get the your unit right, your format right, that data is, you can add it to your databases, your systems to process them. Processing location data is a bit more tricky. Because location data, usually if you use GPS, comes based on an angular values. You cannot just use normal Euclidean distance to calculate the distance between the 2 points. In some cases, let's say in indoor environments with GPS won't work. Collecting lots of location-dependent data and finding a boundary, finding like data in closer proximities, in closer locations, sometimes it's very computationally intensive task. It's not just a bunch of numbers you need to calculate. Actually finding a bounding box, finding an area, sometimes for machines is a difficult task to perform. There are different ways of working with location data. One of them is using something called geohash. Have you heard this concept before? Have you worked with geohashing? Okay, I'll explain some of the mathematical background on it, how actually geohashing works. Do you have any subject actually study this, or you've learned it based on interest? Okay, this is part of this module and part of the examinable content of this module. I'd like you to learn and see how actually geohashing works and what are the limitations of using methods like geohashing. What a geohash does, takes your latitude, longitude information. Sorry, takes your longitude, latitude information and represents that as a string. And based on the string similarity, then you can start, let's say you take longitude and latitude data and you represent it as a string. And based on this string similarity, you can then start looking at locations in a close proximity. Similar to SACS, if you remember, in SACS we were looking at from left to right. If the characters are similar, the locations will be in closer proximity. The more characters you have similar, the closer they are. This is again a symbolic representation. That means you can use, look at the character similarity, you can look at the symbols and see how close they are, how close the locations are. But there are a few limitations. First of all, this proximity of similarity based on looking at from left to right, the character similarity doesn't have any direct conversion to a metric system. You can't say if you have 2 characters similar or 4 characters similar, you are like 400 yards away or you're 200 yards away. There is no direct translation. You can say these points are closer, but you can't directly translate them to any metric or imperial system to compare them. The second thing about geohashing is that when you have the points and if you want to find the exact distance between them, you need to again convert them back to latitude and longitude and then start calculating the distances. But how actually the geohashing works in practice? It uses a base 32 character map. I guess you're familiar with different base representations. Like you start 0, 1, 2, 3, you get to 9, 10. When it becomes 10, then it starts becoming B, C, and you can see it goes up to 31. This is base 32 is 2 power 5 will be 32. It means you need 5 bits to represent this data. Is that correct? You can represent a base 32 with 5 bits. If you have, like, I don't know, binary, you will have only 1 bit, it will be 0 and 1. Here, if you have from 0 to, basically 0 to Z, the characters, you need 5 bits to represent them. Then every 5 bits will be corresponding to one of those characters you have, right? How do we create now a geohash based on base 32? Is a very simple approach. You take your longitude and latitude data, and I'll explain how you're going to convert them to a base 32 representation. Once you have done it, to a binary representation, my apologies, you take your longitude and latitude data, you represent them in binary representations, and you start taking it from left to right, 5 character by 5 character. 5 bits by 5 bits, sorry. Each 5 bits will be corresponding to 1 character in your base 32. What this is going to be? $16. That's an 8. That will be 24. That's a 1. 25. What is 25? Sorry.
13.
13. That would be an E. Yes, sorry. That would be an E. Take the next one. What this is going to be? That's 31. What is the character for 31? Is a Z. What's the next one? 24. And what will be the 24? S. Right?
That question, if you go back, there's no A?
Yeah.
That's supposed to be that?
That's how it's designed for geohashing.
So there's no A in the
There's no A. There are different types of base 32. You can have A.
If this is examinable, are we given this table?
Yes. Yeah, yes. Yes. And if the exam, probably I will give you the binary as well. I won't ask you to calculate the binary. But I would like you to know how that binary is calculated, right? Now the tricky bit is how to get from, let's say, 90, 180, this is your 90 will be your latitude, and this will be your longitude. How you get from something like this, I use the extremes, extreme points. How you get from something like this, from 90 to 180, to a binary representation like this. Can you guess how it's going to work? It's a very simple principle. Someone has a patent on it, but it works based on a very simple principle. If you read the description on Wikipedia, they will tell you geohashing gets the latitude, longitude data. Always starts first with the latitude, longitude data, and converts them to binary, and then it starts doing something we call it bit interleaving. It sounds a very complex and mathematical equation, but once you know actually how it works based on a very simple principle. Let's take Earth. My drawing is very bad. And let's assume this is Earth. It's not a really direct spherical, but let's assume it's actually a direct sphere. This is going to be difficult the way I draw it. Let me draw it something better a little. Okay. Now, if you have a latitude, will be something like this, right? The first one is the equator line. And then you will have different lines here, am I correct? These horizontal lines are our latitude lines. And the longitudes are, the lines are coming like this. These are longitudes. Bits of geography, right? Now let's start with very simple and a basic description of these lines. If I have my first latitude line, you know, it differs between plus 90 and minus 90. Latitude goes between plus 90 and minus 90. If I have something here, can I say this is in my 0 point? And if I have it here, can I say this is in my 1 point? Can I divide it to two areas based on my latitude? Okay. Now if I draw my longitude, can I say if something is on left-hand side of my longitude, which my longitude will go between minus 180 and 180, can I say it's on left is on 1 area, and if it's here on 0 area? And if I tell you now something is in 10, sorry, I'm starting with latitude, longitude. If I say something with 0, 1, which area is I'm referring to? The first bit is latitude, the second bit is longitude. 0, 1, which area is going to be? Will be here, right? Let me show it in a different color. Will be here. If I say something is in 1, 1, where is it going to be? This is 0, 1. Where will be the 1, 1? This is 1, 1 area, right?
No, 1 left.
Oh, sorry. That's correct. This will be 1, 1 area. Is that clear? You divide it based on lines, and each part of the line, if it's like on the top is 0, on the bottom is on the latitude line. On the longitude line, you start saying left or right, and you divide it. Yes?
You said the latitude was first.
Yes.
So 0, 1, wouldn't that be the bottom right?
0 is top in my latitude, the way I've shown it. The whole top area here is 0 in my latitude. This is the 0 area. Yeah? Does it make sense? Now we start dividing this further. Divide it one more. Based on longitude, latitude. Then each of this now, this will be, if you are within this, you will be 0 and 1. If you will be here on the longitude, you start making basically bounding boxes. Add more lines, and each segment you divide it. Basically, you slice it like a cake, then each slice gets sliced and sliced and sliced. What this bit interleaving does, takes one bit from latitude, one bit from longitude. One bit from latitude, one bit from longitude. Go like that, your box becomes smaller and smaller and smaller. If you look at this one, for example, it starts with 0 and 1. This 0 and 1 will be this area. Is that correct? And then continue going further in and in and in. Becomes smaller. Then within this area, the next one is going to be 1. That means within this area, draw another line. And the top will be 0, bottom will be 1, and goes below. Like within that slice, top and bottom. And you make it smaller and smaller and smaller. Do I need to explain this further? Did I explain it very... Is it clear how it works? It's a very, very simple concept, but it's an interesting one. And you have the boundaries, like every time you chunk it, basically you divide it equally, you're started with between 90 to 0, 0 to minus 90. Next time you will be dividing that 90, will be 45, 0 to 45, 45 to 90. Next time you divide it, you are dividing 45, will be 45 divided by 2 will be 22.5. Next time you divide it will be 11.5, and you will make it smaller and smaller. This bounding box will become smaller. You see, the more bits you add, that tiny areas are going to become tinier, tinier, and tinier. Where do you stop it? That's an interesting one. I think this uses up to, how many characters this uses? Look at this normal geohash, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 characters it uses. But you can use The more characters you use, your granularity will increase. And you get to a point, probably the points becomes very, very small. And that will add a little problem if you make it like in some cases. What problem you can think of actually this would cause? This method of actually creating geohashing is very simple, very effective. You can see by bit interleaving from left to right, quickly you go and run it to a smaller bounding box on surface of Earth, and you say, I think it's here. And the next one, which has more similarities, means it's closer and closer. That's why from left to right, when you look at character similarity, you see they are in the same location, because as you start going it, you are basically starting with the bigger bounding box, and within that box moving. It's similar like you're looking at, first you say this seems to be this city, then you're limiting it to district, limiting it to street, limiting it to small alleyways, limiting it to smaller postcodes, and go smaller and smaller. But what do you think could be potentially a problem before I say actually geohash has some limitation? I have a space here to draw. If this is the surface of Earth, if you draw, let's say, let's start drawing a longitudinal lines. When you draw your longitudes, you get closer to North Pole or the South Pole. These points becoming very, very close to each other, but they are different longitudes. Am I correct? Because the Earth is a spherical surface and you are trying actually to look at it some sort of like a 2D surface, you will get to some problem, because when you make these bounding boxes, the areas on North Pole or the South Pole, they will have different characters, they will have different bounding boxes, but they could be very, very closer areas, because the longitudes in two edges of Earth are very, very close, are very narrow areas. Means the bounding boxes here will be tinier compared to bounding boxes around the equator, because around the equator the lines are much wider in terms of longitude. That would be one limitation. Means in the poles you will have a limitation on actually defining, like two close locations could have different geohash because they will be closer. If you fall on one of these lines, they call them median points. If your point exactly falls in one of these lines, actually your geohash might generate between two sides of the Earth. Again, you take two sides, you're trying to look at it as a surface, you might actually get it wrong. And similarly, if your point falls on the equator line, the first equator line, then maybe geohash actually generates it 2 points. Things like closer points could be assumed they're on two sides of the Earth, not the way around. That's the three biggest limitations of geohash. I'll get into them in a minute. And I've asked that a few times in the exam. Tell us what are the key limitations of geohash. But to start with, first you will have latitude, longitude data. And what it does, again, takes that longitude, latitude data. Usually that division of dividing it between these bounding boxes, making them smaller and smaller, is done once. You do it once, you divide it, you have a lookup table, and based on this value, you start saying which part of that lookup table you're going to fall, and you start from left to right. Let's say you start with 25, you say 25 seems to be between 0 to 90, but the first bit will be a 0 or 1, whatever we started, will be a 0. The second bit, you start going in and start creating it. The first, again, you will take what is called bit interleaving. Means 1 bit latitude, 1 bit longitude. Latitude 1, longitude 1. Then the second bit of latitude, the second bit of longitude, and you carry on. 1 bit of each point. Once you've done that, once you have created a representation, something like this, then you start from left to right, separate them by 5 bits. Each 5 bits will be equivalent to one of those characters in our base 32 representation. And you will generate a string representation like this. There are lots of algorithms online. There are lots of web services online. They do this for you. You just give your latitude, longitude data, and you will get your geohash representation. But I wanted you to be very clear how it's calculated. It's a very simple form. If you're on left, let's say 0, 1. If you're on top, let's say 0 on 1. Actually, I haven't checked. Maybe it's the other way around. Just I used it as an example to say how they are calculated. But I guess it's this way. 0 and 1. And then we start making these boxes smaller and smaller and smaller. And you create your lookup table. Yep.
Is there a bit left over? It's 25 bits.
No. If you have 12 characters, you have 12 characters. For each character, you're creating 5 bits. 12 by 5, you're creating 60 divisions. And 60 means 30 across each of angles. 30 across longitudinal, 30 across latitude.
You said there was 3 limitations. The north pole, south pole, being on the first paragraph.
I'll explain the limitations in a minute. Again, I'll repeat the limitations and I'll explain them. It is in my slides. But I just want to make sure everyone has got the idea how we calculate it. I'm happy to explain it again. Do I need to do that? Okay. There's an online service. I use this online service actually to create 3 geohash. I took one as geohash for Guildford. I took the latitude, longitude data for Guildford. I looked it up online for University of Surrey and for Arthur C. Clarke building. Will be the building next to the lake. And these are the geohash. And you can see, for example, for between the Guildford and all the rest of the buildings, we have like 4 characters are similar. The closer they get, they will have more characters and similar. But you can see there is no metric system. You can say, like if you have 2 characters, there are, I don't know, 200 meters away. If there are 3 characters away, you cannot directly transform it to a metric system, especially because they are angular in different parts of the Earth will be different, how many characters there are similar or how many characters there are away. Closer to north or south we move, these points will become closer, the bounding boxes will become smaller and smaller and smaller. Closer to equator we get, especially in longitude, they will become wider and wider in both directions. Yeah? I think one year I've given this figure with this, or geohash without putting the numbers. And I said, can you guess where these points are? We just needed to figure out from the left to right similarity. I think I've given one of the points saying if we are assuming this is 2, where would be the rest? We just needed to figure out the one which close to 2 should have more character similarity. Then you would have looked at from left to right and you would have said this has more characters similar than should be 3. And this is because the distance here is a bit, I don't know, closer. You need, I think I've given 3, not the 4 one, because between 1 and 4 would have been difficult to guess which one it is. Okay. Using bit interleaving and using this mathematical description and base 32 is not the only way to generate geohash. This is an example, again, one of my students a few years ago did. He went and looked at just Google Maps or OpenStreetMaps. This is a map of Palo Alto, San Francisco, I think, yes. And what he did, he took this basically a 2D surface. First, you need to assume every time you do an approximation of a 3D surface of Earth to 2D, you lose some accuracy because you are taking a 3D surface, a spherical surface, you are mapping it to a 2D surface. But let's assume if we have that, then divided it to blocks of 0.6 mile. And it started each of these blocks, gave them a character. And it started with bigger map of the US. This is like east coast of US. And then you make this area, you call it 0, 0, 1. Then each of them, let's say each of the bigger bounding boxes could be like 10 times bigger, like 60 mile each thing. And then you make it smaller and smaller and smaller. Basically, you're dividing it to smaller and smaller boxes. Then the box 0 will be divided to another, let's say, I don't know, 16 boxes. That 16 boxes, each of them will be divided to smaller and smaller. Then if you say something is 0, 0, 0, 0, means this part of the East Coast, within that part you are referring to this smaller area. Within that smaller area you're looking at this small edge, and within that small edge you're referring to the small street. Basically, from left to right, you're specifying where your location is. There are multiple ways of defining it. That geohash, the mathematical base 32, is a more common way, and there are lots of systems with support it. There are lots of web services. I think MongoDB has a feature you can actually use geohash for storing and searching your data. Now the limitation, the 3 limitations we had. One, the areas located on 2 opposite sides of the equator, or the nodes that fall on the longitudinal or median points, can produce geohash that have no common prefix. Let's say if you're very close to equator, but suddenly you fall on one falls slightly higher than equator, one is slightly lower than equator. Let's say if this is the equator line, exactly how we calculated. It could be here, I could be here, but the geohashes will be significantly different because the first bit we started actually dividing it, divided us between 0 and 1. And we started the very first character, I mean, you can see it will be going to be different because the highest bit you are getting, from left to right, that would be your highest bit. The highest bit is going to be different. Does it make sense? And same for longitude. If this is the Greenwich line, you stand on one side of the Greenwich, I stand on the other side of the Greenwich. The second bit, which starts from top, already has separated us. That means if you are looking from left to right similarity, we will be very different. Those are the limitations of geohash. When you fall on very close areas, like on exactly the same lines, and you have smaller distance between the median lines or between the equator line, you might generate different geohash descriptions. Yeah. And North Pole and South Pole are more intuitive because, I mean, if you look at any picture of Earth, when the lines they get to north, they become very close, and the same for south. And then again, we could be standing like in North or South Pole, very close to each other, but we are in different bounding boxes based on the geohash description. And that's when you start increasing the resolution, you're making these boxes smaller and smaller, and the chances of actually separating them. But you add more resolution, then you need also more bits to store them. Okay? But same time is a very effective and very fast way of calculating it. If you do, and I'll show you an example, I'll show you now, if you do calculation based on finding the distances between points, based on GPS locations, based on latitude, longitude data, they're usually computationally intensive calculations. The good thing about geohash is calculating it is very fast and easy because you have your lookup tables and you just calculate it based on a lookup table. At the same time, finding the proximity of the location, sometimes imprecise information are sufficient for your purpose. It can be very effective. Let's say in IoT, you need to know what are the sensors around University campus. You're not looking for a metric like 5 meters distance, you're just looking for an area. And then if you convert all the locations of your sensors to a geohash, you can quickly start find all the sensors on Surrey campus, all the sensors in this part of Guildford, all the sensors in Guildford, all the sensors in Surrey, all the sensors in England, in the UK, in Europe, and you start making it bigger and bigger based on your bounding boxes. Well, when I said in Europe, the bounding box won't be one box, it will be several of them. But you can see, you can easily start widening your search scope for a location or narrow it down to a very specific area. A few times I've asked what are the limitations of geohash. And a few things, again, I will provide this information if I ask in the exam, but it's good to know longitude varies between minus 180 and 180 and minus 90 and plus 90 for latitude. Sometimes if you look at the geographical descriptions, they will use 0 and 90 on each side, but they say east, west, north, south. They will say like plus 90 for each of them, but say 90 south, 90 south, 90 north. Okay. And if I ask what is the concept of bit interleaving in geohash, it's very clear. You convert them to binary representation. You take 1 bit from latitude, 1 bit from longitude, 1 bit from latitude, 1 bit from latitude, because every time you're choosing one area on those boxes, and you make those boxes smaller and smaller. Okay. Now, how to exactly calculate the distance between now 2 points we have in geohash? I said you cannot convert that to a metric system. Then if you really wanted to calculate how far 2 points are, the first thing you need to do, you need to transform it back to latitude, longitude information, because geohash is not a lossy function. You can always reconstruct the original one. You just start it, but you will use some accuracy depending on how many bits you use. You will have a little inaccuracy in precision because those boxes won't be exact location. You will lose some detailed information, but you can, close to proximity, reconstruct your location information, right? If you have only 2 bits, you can only construct it in a very large or very imprecise area. The more bits you add your geolocation, you can reconstruct it with more. There is a loss, I have to correct. There is a loss, but the imprecision depends on how many bits you add. Once you have transformed it from, again, geohash description back to longitude, latitude information, now you need to look at how you calculate the distances between two, let's say, GPS coordinates, between a pair of latitude, longitude. Let's say if I have my latitude 1, longitude 1, and a pair of latitude 2, longitude 2. How do we calculate the distance between them? The simple thing, you cannot just subtract them from each other. If you do that, it will be wrong. And the reason it's wrong because they are angular representations. They are not straight lines, and you cannot just subtract them from each other. That means if you are using location data for clustering, for any calculation, for any proximity, you cannot just use normal distances in your functions. You need to change the distance function to calculate the distances between the points. Have you seen before how you calculate the distances between 2 geographical locations, 2 GPS locations? Okay. Before I continue, is there any question regarding geohash? Because I'm going to change the subject now. I'm going to talk about the GPS locations and how you find the location. Is that clear? How we calculate the geohash, how we create the strings? Is that clear? If I ask a question, why when I say there is a bit of loss in precision when you reconstruct your data, do you know where that imprecision comes from? Exactly, because geohash represents a bounding box, and that depends on the size of that box. The bigger the size of that box is, we will lose the inaccuracy. Let's say all this area will be represented by 1 geohash. Then if I'm here or that end of the room, still will be the bounding box. The more we make this box smaller, the more number of bits we need to represent it, right? Now, to calculate the distance between 2 points, there are different ways of doing it. I chose a little complex one, but there are some simpler ones of doing it. Again, all these methods of calculating these points, they are making assumptions of taking this 3D point and trying to map it to a 2D surface, and on a 2D surface trying to find, or they use angular distances between different points. Depending on what assumptions they make and how they do the calculation, you might have, some of them are more accurate than the others. This is a little more, Haberstein's formula is one of them. It shows more accurate than the other ones. There are other ways of actually mapping geohash to a 2D surface and doing a 2D calculation, distance calculation loss, similar to what I showed in SACS. I chose a little complex one to show actually you can do more precise one. And to do that, do you know sine and arc tangent and all these calculations? Yeah? You calculate an A, which is square of a sinus of sine wave, sine of delta phi divided by 2, cosine of phi 1, and cosine of phi 2, sine square of the delta lambda divided by 2. The important thing is this phi and lambda is the latitude, longitude data. R is the radius of Earth, which is 6,371 kilometer. And delta phi and delta lambda is basically now just the normal calculations of the distances. The important thing is all this calculations based on this phi's and latitude and longitude is converted to radian. It is not in degree. It's an angular representation. Do you know degree and radian? Yeah, it's a radian representation. If I ask something like this in exam, that would be a little complex question, but I will give all the formulas. You don't need to remember any of these formulas. I don't remember them. And I forgot to say, once you have calculated A, you need to calculate the C, which is this is arctangent of square of A and square root of minus 1 minus A, and the distance will be this 2. And if you find it easier to read the code, that's how it's calculated. If you find reading from code is easier, that's how you read it. This is the radius of Earth. Then you take this is the phi, which you take the latitude to round it to. This is phi 1, this is the first one. You take the delta, you take the delta, convert it to radian, and then you calculate the calculate A, calculate C, and you calculate the distance based on that. And imagine if you have now 1,000 points, you want to calculate the distances between them. It's a very computationally intensive task. And if you had we had many sensors, and every time you wanted to calculate what are the closest proximity, imagine every time you needed to do these calculations. That gives you an idea why a solution like GeoHash is a very effective way actually finding proximity of the locations. Can be imprecise, it has its own limitation, but can give you a very fast way of actually doing calculations. One way of looking at it is using GeoHash with a combination of a distance measured like this. That's why I wrote this formula, because I wanted you to be fair. Once you can combine these two. You can use GeoHash, for example, for finding the closer proximities. And then if you really wanted to have the precise proximity, then you have limited the scope of your search. Within that smaller scope, you can use different precise ways of calculating the distance. There are multiple ways of doing it. I added a link. I suggest if you're interested in this topic, go and have a look. This is a good source. There are several other ways of calculating it. Some of them are imprecise compared to this method, but they are much more easier to calculate. In many of the scientific papers, usually you see different ways that people have decided to do the calculations. Two things you have to be very careful. One is your coordinate reference system. If you're using GPS data, the GPS by standard uses a coordinate reference system which assumes where is the center and it starts doing the calculation. I didn't mention it, but it's called coordinate reference system. Especially if you're designing IoT application which your location can come from different devices which provides the longitude or latitude, whatever they are providing as their location from different coordinates reference system, or they call it CRS. Just be aware of it. There are different ways of actually doing coordinate reference system. GPS uses a standard usually one of representative. The second one is in this formula, all the angles are represented in radian. And any new calculation you do, always remember you need to transform them, to convert them to radian. And you see here, this is a JavaScript code, by the way. All of them are converted to radian before any calculation. Just by default, don't take the existing numbers. Not all the methods are, they need to be converted to radian, but this particular one, the Haversins formula needs to be, all your calculation needs to be converted to radian. Again, for the requirements of this module, you don't need to remember any of the formulas, but you need to know the principle. If I really want to be difficult, probably I'll give you a few points. I'll ask you to calculate and find the closer points to each other. I'll give you all the formulas, all the descriptions. Probably I'll give you how you can convert degrees to radian, and ask you to do the calculation. It's just simple math. That actually can be transformed to an easier question. Probably I won't ask that. Okay. Any questions on location-dependent data? A few things you need to remember. Finding proximity of two locations, sometimes you may need more than one point, especially if you are looking for a bounding box. You need to have some reference points. By one point, probably you can take a radius and search around a radius. If you're looking for a box, you need to have a few reference points to find how the point falls in that box. If you're taking that box, always be aware of the borders. If you take this to say this is a box and I want to find all the sensors around this box, and something falls slightly outside your box, could be still in location proximity to one of your corners while it's out of your box. So you need to be aware of that. There are ways of calculating this. You can calculate based on GPS location, based on taking latitude, longitude data, and finding distances. You can see some of them are more complex, and you could just run a course on actually with location-dependent data, searching bounding boxes, how you define bounding boxes. Some of those I didn't go into detail, but there are sophisticated systems that they do this. There are some APIs, some databases you can store and you can find those locations, dependencies or proximities. Another important thing is you can use some little imprecise solutions like GeoHash to convert actually your location data to a string representation and use a string similarity to find the proximity of locations, but you will have them run into different limitations, which we described, that the limitations were on north and south pole, were on the equator line, and they were on the longitudinal lines or median points. Once we have our location data, any questions on this? Okay. I thought it's important because most of the IoT data, most of the IoT applications will be location dependent, and you need at least to have an overview of a location dependency. But I'm saying this on its own can be just a module for the entire semester discussing how you process, how you analyze this data. And sometimes, I forgot to repeat this, you can use a hybrid system. You can use, for example, GeoHash to find the location proximity and then combine it with a more precise method of actually grouping then the locations within that area. But once we have we know how to treat our data, we can store it, we can interpret the location, we can interpret the metadata. So far we have focused on, we started from the nodes, operating systems, how we communicate data, how we analyze it. We looked at the patterns creation methods like SAGs, we looked at change detection, we looked at metadata representation, semantics. And now let's see how we can put them all into practice to create really large scale, not necessarily larger scale in terms of applications, to create different components of a system which can contribute to create a larger application. There are two definitions here. Sometimes people refer to IoT systems as end-to-end, machine-to-machine communications. I try to differentiate a little between these two. Sometimes people use them interchangeably. They will just, when they say M2M or IoT, they mean one or the other. If you want to be very precise, when you talk about M2M, machine-to-machine, you mean the interactions, all the data processing, actuation, everything happens between two devices, two machines. Most of the time in machine-to-machine communication, you take human out of the loop. When you are talking IoT, you're talking more generic applications, which humans, machines, all of this could be part of your ecosystem. Applications of IoT, there are various areas. One of the rapidly growing areas is industrial automation, or sometimes you will hear it as Industry 4.0. It's just a trade, I mean, it's just a trademark people have put on it, but generally refers to using Internet of Things technologies. And several other areas. I'll provide today some examples on healthcare, smart homes, and smarter cities. But again, each of this can have we can have long discussions of actually how you implement system, what are the current examples. But typically, the applications in IoT, either they are designed to detect events, When I say detect events, then you might respond to those events. You're monitoring something, you're monitoring for healthcare, for changes in the signal, for changes in the environment, and then the data collection, change point detection, which we discussed briefly when we were discussing SACs, becomes important, and how you create patterns from that data and how you find anomalies. When I say anomalies, could be anomaly changing the data or could be the noise as well, because most of the IoT deployments are in noisy environment. Many applications will rely on periodic measurements. You're collecting data based on a certain frequency. We discussed some protocols like MQTT, how you collect publish subscribe mechanisms, how you subscribe to an event, how periodically you collect data. We discussed some of these periodic measurements could be based on fixed sampling periods. You say collect data every 5 minutes. Or sometimes you might have adaptive methods of doing this. Depending on how the environment changes, you might start changing your frequency of sampling. Think of whether you can implement that in your coursework. Sometimes IoT applications can work in collaboration. We discussed the node-centric programming, application-centric programming in the past. We said different nodes can collaborate with each other towards an application. For example, for edge detection, if you're deploying it for monitoring fire in forests, then what you do, you're looking at wind direction, you're looking at the fire direction, you're looking at the heat, light, and multiple sensors can help you to get a proximity of how that event happens. When I say you, this information can relate to from different sensors, and a machine can basically analyze that and finds the edges which that event happens. In an industry, it could be you can put a noise sensors on all your machines, and depending on the changes of the noise, the vibration on the devices, you find which part of your machine seems to be malfunctioning or has a risk of an error. And if your sensors become mobile, or you have multiple sensors around the path, you can start also tracking a mobile event or mobile object or whatever it is you are monitoring it. Usually you have a set of sensors. If I want to really oversimplify how an IoT design in a larger system works, and you have an environment which you are interested in monitoring that environment, the sensors start collecting data from that environment, basically they sense that environment. You have then a set of controllers. This could be like data analytics, machine learning, AI, whatever processes, or you could just have a simple dashboard. You show that data, someone takes an action. That action will go back to the environment. Could be, again, you just notify a human. You say, for example, you're monitoring for health. You'd say a clinician, some of your patients could be ill, or it could be you're monitoring for fire. You just generate an alarm, which is a sound, or it could be an automated, again, a machine. Could be just based on looking at if no one is in this room, switch off the projector. A very simple scenario. And usually you have then again another loop. Once you have switched off the light, switched off the projector, another sensing you will do to get whether it's off, and you start controlling it. Usually it's a loop. Obviously not all applications will have all these components, but this is a very generic architecture for IoT applications. Now, once you have that requirements to start actually designing your application, you need to look at what type of services you need and what characteristics for that service you need. What type of data model you need. We discussed the heterogeneity, talking of creating interoperability in IoT systems, how much autonomy you want those services to have. You are programming your devices, your IoT resources to have fixed actions, or you want them to become more adaptive to what changes in the environment. Depending on your design, depending on your requirements, and your resources, you might have different solutions. Data processing, again, what type of, once you collect data, how that data is going to be processed. We discussed that can be processed on the device, can be processed on the gateway, can be processed in the cloud, can be distributed process, can be exchanged between different nodes. All of them, again, becomes part of your design. And as we discussed earlier today, the quality of that information, accuracy, delay you have in collecting information, delay which you have in your network, how you actually, how reliable is your platform is, depending on your application and what you're monitoring becomes a part of the criteria for designing. In larger scale applications, especially if your deployment is in the wild, the fault tolerance and maintainability of that becomes important. How reliable is the platform is, depending on, again, if you are using it for a sensitive application, and the lifetime. Energy efficiency, how much energy the nodes they use. You can make it again more adaptive. You need to think of when you deploy a sensor for a set of sensors and actuators for how long they're going to work without you requiring to go and change the battery to maintain them. Or if you don't need to maintain, we discussed, can you remotely go and update them? Can you change them? The policies of maintaining them become important. Within the remaining half an hour, I'll try to give you some examples, actually, how you come across these problems in real world. Before doing that, then there are some key characteristics. The solutions you create, how they're going to scale. If you're scaling, we discussed the interoperability issues, the data analytics, the scale of the processing it. The density of your deployments will make a difference in the accuracy of your data, energy efficiency, and other parameters you do. If you put one sensor to measure temperature, it will give you an imprecise measurement most probably. Depending on where you put it, also will become very important where you put that sensor. If you put it closer to that projector, the temperature you are reading from that room will be different if you put it, I don't know, somewhere in that corner or that corner or that corner. The design characteristics can also confuse your applications. Once we were deploying sensors to monitor people's daily activities, and we started using PIR sensors. They are the infrared sensors. When you pass, someone passes through them, they just send information to say, well, there is a movement in that area. Quickly we realized if you deploy the sensors in a certain angle or a certain height, if you put it in too high, but you will lose lots of movements around the house when people move around the house. If you put them low, if they have a dog or cat, completely your system will get confused by a pet running around the house, and you will find it very difficult, for example, to read people's daily activities because your data will become too noisy by just having a pet around and running it. Then part of the IoT systems, whether you like it or not, becomes you need to think of the environment your sensors are going to be deployed and the characteristic of that environment, because they will have an impact on your application. And we have discussed programmability and maintainability. How easy it is to maintain your system, to update it. Like in Contiki, we discussed there are some features in Contiki. You can do dynamic programming, you can load your program, change the program remotely. You need to think of those characteristics. And obviously, if you are using wireless communication, whether your nodes are directly connected to the node, or they need to have multiple hub to communicate to that. Dr. Fo and I, in the past, we have given like an example. I think in week 10, if you come to the review class, we will provide you an example of that. One year, the exam question, one of the questions was, we gave a scenario of a farm, we gave the dimensions of the farm, we gave a number of sensors, and we said we can use one gateway. Where do you put this gateway to make your network more energy efficient? You needed to think of multi-hub communication. We gave the range, how far the sensors could communicate, and not all the sensors would have gone directly to the gateway in that scale of the farm. You needed to think of a design which would have maximized the lifetime of your network. And different solutions on how the nodes can collaborate. The solutions are usually data-centric because you're interested often in the data. And most important thing in the design, security, privacy, and trust. If your system is not proven to be secure, if it's easily hackable, or if you cannot prove it's not easily hackable, it will be very difficult to deploy lots of these applications. Security, privacy, trust will be the concept of next lecture next week. Dr. Fo will talk about it. And obviously, different applications will have different requirements depending on what application you are looking, what domain you are looking, what resources you have. You might consider a combination of these features. Sometimes you might need all of them. You need to make adaptive. You need to look at mobility. You need to look at the data quality. Sometimes in some applications, you might need a subset of these applications. One important aspect, again, in creating IoT application is if you're relying on crowdsourced data, sometimes the reliability of that data, it can be an issue, or it's important you are aware of it. This is an example of a few years ago, I think around 10 years ago, when there was the tsunami and the nuclear leak in one of the power plants in Japan, in Fukushima. what happened is a group at MIT, they published basically a description instruction telling people how they can use their iPhones, they can use their smartphones, connect some sensors to those, and use those sensors for monitoring the radioactivity level. And back then people used a platform called PatchBay. I think now it's called a company called Xively. And people could use an internet, a Web2 application, basically a platform, to publish the radioactivity levels in their neighborhood. That was a very good example of IoT, crowdsourced IoT. Before actually the government agencies could then deploy their sophisticated sensors, their information, people actually could use just what they had, a smartphone, put some sensors, put outside their window, and monitor and say the radioactivity levels. An excellent application, how we can do like interesting application using crowdsourced IoT. There was a problem. And the problem was, back then in some areas, if you went and looked at the information, if you actually drilled down to look at the details of this information, some people were reporting significantly different readings from their radioactivity levels. The reason for that was not because people did it on purpose. Some of those devices were not calibrated correctly. Some of them were not put in the right direction. Some of them, the programming had some problems. And that shows the issue of, if you rely on crowdsourced information to generate an IoT system, you should always be aware there could be some quality issues. You need just to have some mechanisms or some ways of either say, determining the trust and reliability of data, or at least be aware your data can be easily biased. Other sources like we have used in the past, for example, Twitter data to extract traffic accidents and traffic information. But you can just, if you're, you have like class 9 in the morning and you're rushing to drive to A3 and you think it's going to be busy, you can get 10 of your friends and write a program to tweet 10 times. Let's say there is an accident in A3, and our system can pick it up, and you can easily basically make this information biased. If you're using crowdsourced data, you have to be always aware of the quality issues and the trust and reliability. Now some quick examples on applications in smart cities. But one of the key drivers for people looking at IoT solutions for smart cities are basically the problems most of the big cities or in the smaller scale cities will face. I mean, in terms of the space, in terms of the air quality, in terms of waste management, in terms of the resources they need to run their cities. And IoT-based solutions seems to be more interesting and promising solutions to manage some of this city infrastructure or provide information. Like I've seen some interesting examples of the bins of trash bins around the city. For example, when they get filled up, they send a message. Instead of then sending people to, like on a regular basis to go and empty them, cities can optimize their resources. When the bins they get filled up to a certain level, they send a message, and then you can manage your resources better to go and empty them. There are lots of examples of how actually you can use IoT technologies to make cities smarter. We had a project, I was running a large project around 2012-13 we had, and that was the first time I started looking at IoT applications and IoT for smart cities. And when we started that project, I was just interested in seeing what people were thinking about smarter cities like 30 years before us. Well, how people serve the cities. And I was thinking what we are thinking, people will look 30 years from now and will look at our view. And I went on a little bit of search, looking at what people were thinking cities will look like. Let's say this is an article from LA Times saying how Los Angeles will look like in 2013. And that's around the time I found the article. And this article was published in 1998. That would be, how many years? 20 years? 20 years ago. 30 years. When we looked at this, I looked at this article, it was interesting. They were assuming this will be, these are like 400-story buildings, and these are electric cars going around like city. A robot makes your lunch, and this was the assumption in around like 20 years ago, looking at how our cities will look like in future. Then I went and did a search on Los Angeles in 2013. That's the real Los Angeles in 2013. In average, I think each person spends something around 4 hours of their life in traffic jams. There are huge problems. And that was a good lesson for me to understand actually most of the problems we are trying to solve are there. I mean, the problems have been there for decades. What has changed is the way we can collect information, the way we can interact with our environment. Then sometimes when you have a new technology, you don't need to think of a spaceship to create an interesting application. You just need to look around the environment you work, the industry you're going to work, and think of what you know, the technologies are available, how you can make that better. That's Guildford in 2013. And you probably can recognize this area. That's where the Debenhams is, and this is the roof of a car. We had a flood in Guildford around the same time, and River Ray flows here. You've seen the river is just behind this building. And that's again a reminder of, that's where this alleyway where the Apple store is. Most of these problems, like the flooding problem, has been around for decades. What has changed now? We have sensors that measure the rain level. We can actually get probably from the environmental agency this information, or we put our own sensors. We can put sensors on the river, on different parts of the river. We can communicate this information. We can close the near real-time monitor between the rain, between the increase of the rain level, for example. And sometimes by just putting this information together, you can warn people, you can warn the city council, for example. They put this in 2013, but probably a bit late. Once it happens. The problem is often you don't know these events are going to happen, and once it happens in multiple places, and reaction to that you need to be more coordinated. And sometimes like using simple solutions like IoT solutions can actually warn us people earlier about these events, can help them to make better decisions. Doesn't need everything to be automated. Sometimes it's just the information you collect, the way you process that information can make people to make better decisions. You can think of various applications in IoT, like in traffic, waste collection, looking at the transport, looking at noise and air quality, especially like people with respiratory conditions like asthma, like for some of them the pollen levels, the air quality level is important when they travel around the city. And these things changes during the time, during the rush hour, during the different times of the day. Imagine if you could give those information in near real time to people as they travel, as they go around the house. Looking at the security, different applications you can think of using smart cities. One thing is, most of the cities, if you look, they already have this data. Often when the cities I have worked with, most of them, they will have this information. Again, often this information are collected and generated for different purposes. At least the current state of most of our cities is they have information about the waste collection, about the traffic, but most of the information are sort of offline collected, processed, becomes reports, people read it, or some sort of offline mechanisms of providing that. Even some cities, they have online data stores, but if you look at most of the data stores are not real time. They get updated like based on different frequencies. I don't know if you have come across, London has one of the biggest data sets on smart city or city related. It's called London Data Store. I think they have over 500 data sets. Some of them actually they get very regularly updated, and there are lots of interesting information there. One thing IoT has changed is the speed of this data. Now this data becomes available almost in near real time. The processing it, the accessing to that information has now rapidly changed. Now we don't have the information about waste collection every month. We can have actually state of the bins around the city every single minute, depending on how we program it, what resources we put to use and measure them. And that makes IoT very interesting. Again, like using traffic information. Most of the traffic sensors, there are, I think, a lot around Guildford. I've come across a company was doing it, and some of them, they will scan your Bluetooth and Wi-Fi signals. As people drive, they scan for signals of Bluetooth and Wi-Fi, and they count the number of cars. They give you the velocity of the cars. They just put a few sensors alongside the road. And obviously, you will have some, you might say, not everyone carries a mobile phone, or not everyone will have their Wi-Fi or Bluetooth on, but in approximately, they're getting an approximate information. And also, you can say if someone, like, if a bus drives around, you might read like 50 cars passing, you will read 50 signals. Then there are different methods of in deployments. People try to eliminate that noise and improve it, but most of them will use some technologies like that which are cheap. Yes?
Surely for traffic control, it would make more sense to leverage Google APIs for traffic because everyone's going to be on their phone instead of using sensors because you don't have to maintain those sensors, whereas leveraging social media or obviously Google APIs.
That again is one way of doing it. The only thing you have to remember with the Google API relies on people who actually use Google platforms and they contribute to that data. Then again, based on the proximity, it will give you approximately good information, but it relies on a number of people who use, like let's say, I don't know, if you have an area which everyone drives around and everyone has an iPhone, I don't know how to, I haven't checked that actually against exact traffic, but I agree with you. Some of those information are accurate. Again, if you're designing for a smart city and you're designing for as a public authority, you don't want to also rely on a proprietary say this unless you have a data agreement with that. And sometimes that data with a few sensors in it, they can complement each other. Like you might not be too expensive to put sensors everywhere in all the roads. Then you can rely on something like a Google API, but you have sensors in areas which are more important for you in traffic. Let's say if you're monitoring traffic for Guildford, probably you have 10 streets, you get the most congested, let's say, traffic in certain times. You can put sensors there to get more precise information. For the rest, rely on crowdsourced information. But that's a good point. Like traffic information, parking information. These are like very typical examples of people using. I think there is a company provides that smart parking services. I've seen the company. I don't know whether have you seen the service? It gives you smart information on like near real-time information about the available parking spaces. There are different companies focusing on different applications. One thing is important about smart cities. Always think of the scale. What you're designing, how it's going to scale, who is going to use that data and how they're going to use that, especially if your job is creating that infrastructure, and how you're going to update that data, how you're going to process that data. Again, working with cities, I've come across lots of cities, they have a data portal, they get data, like some of them actually publish the data, like I've come across like in PDF. Well, interesting, but if you're using an API to process that data, PDF is not your ideal format, is it? And often this data actually is stored in databases, but when they want to publish it, they publish it in different forms, which makes it difficult for application users to be able to use it. And different audience, especially when you're designing it, you just don't design it for techie people who have certain type of, I don't know, Android application, an iPhone application. And this should be something which more people can use it, a wider audience can use it. And also, the more and more applications collect data, I mean, obviously GDPR has now made it more difficult in this part of the world to collect personal data and how you treat it, which is a good thing. But generally, it's better to specify to people how you're going to treat the data, for what purpose you're collecting it, for how long you're taking it. And by law, you need to comply to most of these laws anywhere. In most parts of the world, you need to comply to those rules. Again, an interesting element of the design, most of the time when we design applications, we talk about success. We talk about saying, if you put this, how it's going to work, what's going to change. Like most of the smart city applications will portray you something like this, to say how interesting they can make their cities to look like. Again, it's better to think of also the scenarios. What happens if it didn't work? What is my alternative solutions? What, again, going back to the reliability, fault tolerance of system, and also the cost of it. Just to use an example, around 2014, yes, IEEE published an article about the city of Detroit. Detroit is a city in Ohio in the States. And I don't know if you read the news around that time. Detroit went bankrupt a few years ago. It's a sad story of a city just becoming bankrupt. And I actually wrote a story about the state of the city. Like part of the emergency services back then, apparently they were using fax. I heard that, I read it. I said, who uses fax anymore? And then imagine if your fire service uses fax to tell another fire service, oh, come to help me, or dispatch some messages and information. That's not ideal. And the city of Detroit around that time was looking to upgrade their IT system. And that was around the time I had started working on smart cities. And that suddenly clicked something in my mind, thinking of, most of the systems we generate, we never think of the cost of maintaining it, cost of actually building it. You always are thinking of the successful design of creating it, but if you're becoming a designer, you need to think of it. And in Detroit, the story was interesting because they went to their bankruptcy judge and asked them to release some of their assets to go and upgrade their system. In 2014, the bankruptcy judge for the city of Detroit has released around $100 million of their assets to go and upgrade their IT system. And IEEE's article was around, out of 100 million, they had estimated around 16 million would have been the cost of running the system, means the human resource of running the IT system. And 86 million they had, or 84 million, they had to go and upgrade their system. And with 84 million, they couldn't buy a Class A IT system, a simple IT system to run their system. They had to go and opt for a Class B. Instead, they had to go an older generation because the IT systems were very expensive. And IEEE's article was around that, how the cost of IT systems and something which we design the systems when we make it complex that we often don't think about. When you're designing an IoT application for any industry, something which you think you're going to stay for there a little longer, think about it, because if that becomes expensive and becomes difficult to maintain, maybe you need to think of changing your job. Another thing is accessibility of the system. Again, this is not part of, but it is. I want you, if you go through this module, to think of this elements of your design when you're designing IoT systems. This is before Google started adding London transport to Google Maps. Now, if you live in London, you have, I don't know, Google first, you get the bus information and things on Google Maps. Most of the cities you will have it. This is a few years before that. And around the area, I live in West London. Around the area I live, in most of the, here also you have this smart, I don't know, screens. Well, smart, it's just a screen will tell you what time the bus is going to arrive. Around the area I live, we don't have that. And I used to have a mobile application which told me what time the buses are going to arrive. And for a minute, let's imagine everyone has a mobile phone, which is not true, and you need to think about it when you're designing applications. But for a minute, let's say everyone has access to a mobile phone. One day when I switched it on, I opened my app. That was, I think, in the evening, and told me, I tell you the first one, and for the rest, you have to pay. And imagine this information was available for free and everyone could use it. Suddenly, by creating an IoT system, you start creating a digital gap. If I pay, I can park better, I can live better, I can get better information, and that public information suddenly gets excluded from a group of people. The same can apply to digital literacy. How competent people are in using IT technologies. If you're designing an application, you need to think of, make it more accessible to different groups. With different requirements, with different accessibilities, with different age groups, different demographic. These become important in designing applications, especially IoT will have lots of applications in public areas. Some examples. This is an application my colleagues and I we worked on it. This is the city of Aarhus. This is the second biggest city in Denmark. This information actually, if you see, I don't know how visible they are. These are the contrast of the colors shows the traffic information. In fact, the traffic data comes from Google API. We are reading and showing a live map of city of Aarhus. And the 3D map was built in Minecraft, the game. Actually, you can drive into the city, you can dive, you can see the buildings. It's made up to scale, like you can actually have a 3D view of the city. And then we started feeding some of that data, which were available on City of Aarhus's data repository, and created an engine behind it, which started analyzing that data near real time. For example, they were collecting air quality information. Now we took that air quality information, we took the pollen levels, and as we travel across the street, we tell you where the pollen levels are high, where the pollen levels are low. If you're choosing a path to drive, we tell you what are the most congested areas in terms of air quality. And that changed the way you look at the information. It's just an example of you can take existing information and make that information better way, more automated way available to people. And then people could subscribe to different events if they were interested, let's say, in traffic events, in air quality events, in different social events. And as they were traveling from a point A to B, the system starts generating events as you go along, as the events appear. If something like an accident appears, just pops up on your screen. While we were doing it, a group of my colleagues at the University of Osnabrück in Germany, they worked on looking at the quality of data. Again, that shows how design can impact your IoT system. These circles, each of those circles shows a sensor network, a bunch of sensors deployed in different parts of the city. Most of the sensors will give you the traffic information, number of cars, velocity of cars, will tell you some information and parking, available parking areas. One thing we noticed, my colleagues were using a formula of like time stamps, looking at the frequency of samples you get, how many samples you get. Each sample, when it's measured, has a timestamp, and when you receive it, you can look at your time, and they were measuring the delay, how long it takes to get that data. And they had created a formula looking at the combination of these variables of, I don't know, delay, frequency, different things, and were generating a quality metric, saying, what is the quality of data we are collecting at different parts of the city? And the greener they are means the quality of the data is higher. The darker red they become means the quality drops. Once we created this system, they created this map, and we started looking at data, and we were creating a demo, and we started noticing, my colleagues and I, we started noticing, when you start in the morning, it seemed all the points were green, and by the time we were getting closer to midday, most of the nodes were becoming darker and darker, darker red. And we're thinking, what's wrong with the sensors? They seem to be in the morning, everything works perfect. By the midday, most of them, it seems, are not sending information. We discussed it with our colleagues in City of Aarhus, City Council, their equivalent to City Council. And it turns out most of the sensors are deployed on lampposts. And they use the power from the lamppost to recharge their battery. And this was summertime. If you're in Scandinavia in summer, the lamppost probably would be on only for half an hour a day, because they had around 23 hours a day daylight or something. And when the lampposts were switching it off, they actually were cutting off the electricity across like a road. It means the sensors we had, they didn't have enough time to recharge them. No one actually had noticed it when they had deployed it until we built that system and we visualized that data. That gives you an indication. Sometimes visualizing your data will give you some really good clues of actually how your data looks like. And that shows you also a design element. If you're designing it for an environment, you need to think of the environmental variables. There wasn't anything wrong with the design, but probably that company who actually deployed it was deploying it in other parts of the world. And I think if you don't go to extreme north or south, you are okay. But if you're deploying in Scandinavia, you have to think of dark nights and very bright days in summer. If you're deploying it, for example, for agriculture, you can look at humidity, you can look at acidity of soil, and all this can be used for different like fungal disease, for different information. It's not just looking at irrigation system to say when you should water it or when it's dry. It can actually give very precise information, and in some of the agricultures, in some industries, is extremely important, this information. And then you can get, again, near real-time information for them. An example of a healthcare application. A few years ago, we started, when I say a few years ago, 3 years ago, I was lucky enough, we worked with a group of really amazing people to create an application for a healthcare. And the area we targeted is working on Alzheimer's and dementia. Again, it's an example of how you can use simple IoT technologies to create something really highly impactful. Dementia affects something around 850,000 people in the UK, and worldwide there will be millions of people. And at any given time in the UK, 1 in 4 hospital beds is taken by someone with dementia. And 22% of those hospital admissions are due to unnecessary causes. Well, not unnecessary, so that's it, due to, sorry, I have to correct myself, my wording, preventable causes. You can prevent those hospital admissions. And we wanted to create an IoT application which can monitor people in their home and can start looking for the signs of what you can use to prevent those unplanned hospital admissions or avoidable hospital admissions. I'll focus here on the technology because this is the technology part of it. And first was, actually, if you want to create an application like that, what is the infrastructure? The first question my colleagues and I, we had, if you want to create something like that, what do we need as infrastructure? It's just saying we cannot just go and put a bunch of sensors. We need to think of the infrastructure. What are the interoperability requirements? Security is important. How are we going to govern data and scalability? Going back to my first question this morning, these were our key design criteria when we designed our system. The first thing we were using sensors coming from different providers, different manufacturers, and we wanted to have to give choice to our participants to be able to choose the devices which they found comfortable. Like we were monitoring people's blood pressure, we wanted to give them choice to choose between 3 brands. The problem is, if you have different brands of different devices, they will send information in a different format. They will have different ways of formatting data, different units of measurement, presenting it probably. And the first issue for us was interoperability. Obviously, we have discussed this. We created, we looked at interoperability, and we looked at how doctors, they store clinical information. It turns out there is a clinical standard called HL7, if you're interested in, or FHIR, F-H-I-R. And they use, I've talked about it before, they use a vocabulary called SNOMED. This is your model, and this is your vocabulary. First thing we did, we created a model which was compliant to HL7 and FHIR. That meant the data we are collecting can be linked to people's primary care, the doctor, the GP records, and the clinical records. The second part, we used the vocabulary to describe that based on standard, which increased the chance of interoperability. The most important thing is, when we work with different companies, we had a common language. All the devices, they send their information using this common language, using this semantic format. It means the platform we were creating became independent of the devices we were using. If you are using, let's say, today, 3 different types of blood pressure monitoring, tomorrow if you have a better one, as long as that data is sent using that format, for our backend platform, it doesn't matter. The device change, but the data remains the same. It means we also make our system flexible and interoperable. That also allowed us to work with different companies, with different providers, and already help with scalability. In terms of infrastructure, what we have, we worked with a group of doctors to discuss and decide, and also we worked with a group of patients and their carers, what devices are important. These are your markers, what you're going to sense, or what markers you have, depending on how you say sensors. This is usually a discussion with the experts, and sometimes some exploratory work to do that. Then each device sends their information using low energy Bluetooth, and you have a gateway model, which stores the data. And then we have a set of backend servers. These backend servers, they basically store the data, bring the data from different sources. And then we have a set of machine learning algorithms which they analyze that, and there are different standards. For example, next week you will study this, where we are using like PKI, if you're familiar, different security encryption mechanisms to store that. Dr. Fu will talk more about that. We took how you anonymize data. For example, in the databases we have, there are some personally identifiable information, my name, where I live, my age, my medical condition. We store that in one database, everything encrypted, and in each person I get a random ID. Let's say we use 128 bytes of information to generate an ID. And any data is collected related to this person, physically stored in a separate database. The idea is, if you hack one of these databases, you won't have the other. And they are physically stored separately, and each of them, they will have their own security mechanism. But at least you are, again, every time you are just reducing the risk. Getting it close to 0 is always, in theory, but practically there is always a risk of error, a risk of a security threat. You're just maximizing the way you're encrypting or basically preventing access to that information. There are different ways of governing this information, but one thing is important. Once we deployed this, the first group of patients we started monitoring them, was around Christmas time 2 years ago. Before December, you probably haven't been here, or some of you might remember, we had a power cut in the university right before Christmas 2 or 3 years ago. Someone drove into the power line, at least the building we had, the servers, we had UPS, and the server ran, like, our servers ran for half an hour, and then they went down. And we had real patients behind it. But we were lucky, we had only 5, we had only started taking it. Again, fault tolerance became a crucial thing in our design. Initially, probably we should have talked about it more carefully. I teach that, I should have thought about it, but I must admit we hadn't implemented that. Now, for example, we have a system which uses most of the service providers will have something like that. We have built our own. Physically, we have, let's say, servers in parallel. They distribute the data. Every data you store is just directly replicated in 3 databases. We have a controller. If one of our servers crashes, the other one takes over. For our end users, completely transparent, but sometimes we have infrastructure failure, but usually the other one takes over. Then you have now machine learning algorithms and things, gets into the details of implementation, how you update the parameters between the different servers, how the algorithm takes over, has the most up-to-date parameters and things, but you can implement them once you have designed that. And the end was, once we collect and use this information goes to different people, goes to the carers or people with dementia, goes to healthcare professionals, and also goes back to us to analyze that data and train our algorithm. For each of these applications, we have created different ways of interfaces, different ways of interacting it. In principle, we are collecting raw signals, we do machine learning, and then we have human in the loop, which they are a group of clinicians. Like, we collect data, we say if someone has an infection, for example, or if someone has a risk of a heart attack, someone has a risk of fall, we look at people's day-to-day activities and we decide if their routine has changed. And then we have created an interface to be able to communicate that information. That interface, again, is important because how you send that information, how you communicate that information is very important. These are just some examples. These are like vital signals. We are collecting like people's, say, blood pressure, pulse, body temperature, and just some simple statistical measures are outlined to this. These are just, in terms of technical implementation, are simple. For example, when you collect information, we learn what is, let's say, I could be in an upper boundary of a blood pressure. Still, my blood pressure could be normal, but a little higher than what it should be. And the system learns this and learns the average, let's say mean, and standard deviation. And it starts looking at now how people change from what is their norm. Because you have now continuous data, you can start looking at the changes from where we have started. And those changes can generate alerts. For example, if my blood pressure used to be on a certain level, which seems to be normal for me, was slightly high, now if I start going higher than what was already, that could be an indication of like some healthcare issues, and we generate some alerts based on that. And when you start, we have worked with doctors, for example, to learn what are the ranges, and over time, the machine learning algorithms, well, machine learning is a bit of stretching the truth, is exaggerating it, just to say statistical analysis algorithms, in this case, will actually learn what are the personalized thresholds. And now you can think of the scenario in different applications. You collect data, and your IoT system adapts to make it more personalized solution for a specific problem. I'm not going to talk about the probabilistic machine learning here, but one of the algorithms is we deployed sensors around the house, and we started monitoring, for example, electricity use. We are using a sensor which you put in power plugs, and when people switch on different home appliances, you detect what it is. For example, when people switch on the kettle to make, I don't know, tea, coffee, and we start finding all those, when people sit on a chair, you put pressure sensor, you read people sitting on a chair, when they walk on a corridor, we put PIR sensors, infrared sensors, we look at movement in different parts of the house. Basically, the system starts looking at the activities. Let's say if this activity is making tea, I'm using an example. If this is sitting on a sofa, you can use, this is going to kitchen, for example. And this is, I don't know, going to garden. Imagine you can put sensors to measure all of this. We monitor people's activities based on the sensor measurements for 2 months, and we learn what is the probability of going from one activity to the other. When I make a cup of tea, what is the probability I go and sit on a sofa? Well, what is the probability I go to kitchen, or I go to the garden, or I leave the house? You collect information over time, you start monitoring people, you learn all these probabilities. For 2 months, we let the system just observe this information, create this state model, and learn the probabilities. Let's say for 2 months, for 60 days, you have seen when I make coffee, what I do. I go and sit 40 times on a sofa, 40 out of 60, I go 75% of the time. The chances of 0.75, I go and sit on a sofa. 10% of the time, I go outside to garden, but you have never seen me leaving the house. Once we have run it for 2 months, we leave it for another 2 weeks to see how much people deviate from that, because people usually will have a little of deviation in day-to-day activities. Once we learn that, we learn what is the normal deviation from the activity. Once you have learned that, you have a system that has a good indication of patterns of daily activities in people. And then you look at how much your system gets surprised, and you measure the element of surprise. Now, I'm not going to go to technical details of it, but if you're familiar, you measure entropy. Entropy is a level of surprise in the system. If the chances of the probability of I do something is very low, entropy will be very high. Let's say every time I made a cup of tea, if 75% of the time I went and sat on a sofa, 10% of the time I watched TV, but the probability of going outside the house was close to 0, that's a huge entropy in a system. And that entropy will give you a measure of if people become hyperactive or less active. The low activity could be related to different healthcare applications. Hyperactivity can be related to different. I'm not going to go to the healthcare issues of it, but that thing again shows you by collecting some, and these sensors are cheap and usually widely available. The value of doing something like that was the combination of creating different markers to be able to collect data, to create the right infrastructure and the right analysis behind that to be able to solve a problem. And that's how we show this information to clinicians. Each home will appear like a card. And depending on the priority of the events, let's say in some house, if someone had a fall, this automatically would go always on top left of the screen. Then your clinicians can monitor hundreds of people at the same time. And if everything is normal, these cards will minimize themselves automatically. They will become minimum. And based on the priority of the events, they will reorganize themselves. Then again, that was a way of creating a dynamic and adaptable system. And if something is serious, they start blinking and changing. Again, different interactions you create to interact with your audience and for user interfaces. Just to sum it up, if you're designing it for healthcare, probably reliability becomes important. Security and privacy and trust, privacy and trust becomes the core. And then you need to think of other requirements like power consumption if you're using for critical things. If you're measuring fall detection, communicating that information, the delay is extremely important. Like you need to send that information as soon as you can. But if you're collecting my daily living activities, you want to learn my patterns and you're going to analyze it on a daily basis, and if communication is expensive, you might aggregate it and send it on a daily basis. Then each application, each subcategory in application will have different requirements. If you're using for automotive industry, for example, obviously you have highly mobile sensors, highly mobile sources. This here now is now near real time. You need probably milliseconds, or I don't know, picoseconds. You need to make a decision, and the delay of your network. That's why 5G networks working on it, decreasing the end-to-end delay, because that's important for real-time applications and quality of service. If you're using it for smart cities, reliability, because you're deploying your sensors in the wild. If you have bins which they can say report how full they are, the reliability of those sensors, they cannot be easily let's say tampered, they cannot easily break down. Fault tolerance of those systems become important. Then each application area will have its own requirement. I think one year I asked this as an exam question, but read it as a practice question for like a few minutes. Read this and just let's quickly overview this. It's a very simple question, and I took it from an application. It's a pipeline and under the sea. Imagine it's difficult to get. You need divers to get access to this pipeline would be very expensive and sometimes very, very difficult. Now, we are interested in putting sensors to monitor leaks in the sensor. What type of sensors you will put to start with? What type of sensors you can think of can help to detect leaks in this pipeline? Pressure sensor. If there is a leak, the pressure will drop. And then you need to think of what is the proximity of the sensors, because the pressure will drop at different parts of the pipeline differently. And then you need to look at what the range you want to be, how far the sensors are going to be. What else can you monitor apart from pressure? What is flowing? You can put like sensors which are sensitive to chemical compounds going into that. If like, I don't know, is oil, you can put sensors which are the density or chemical interactions of it gets into the water. What else you can think of? Temperature, sometimes in the pipelines, inside and outside, temperature is different. If there is a liquid, and each of them will have a range of application, because if like it's North Sea, probably by the time your oil comes out of in just a few short distance, probably will become very cold, I guess. Then yeah, but temperature is a good indicator. You can think of, I don't know whether undersea will work, like acoustic sensors, because the noise and acoustics will change when you have a leak, and you can use something like that. I don't know whether you can use like radar type of technology, because the density of material will change, but those type of things can be also tampered by fish and marine life. Okay, if you do that, what parameters we said, what type of sensors we discussed, what components you will add to this diagram? Or do you think it has all the elements you need? You can add gateways here, because if the sensors are apart, not all of them, if they want to send their information to a base station, the cost of energy sending it, the cost of communication could be higher. They can send it to gateway, and the gateway doesn't need to send information unless you detect a leak. Then you can save a lot of energy doing that, and you can use more short-range sensors in a closer density. Will you add anything else to the network? Of course, you can say processing units and things, but gateway was the most important one. What could be the key issues in you designing something like this? What key issues you can think of the design? Reliability can be an issue. Maintainability and lifetime can be an issue. Once you put those sensors there, it's not easy to go and change the battery. Energy efficiency will be an issue here. Especially here is an obvious case. You can't have, most probably, you can't have direct power, like plug them to power and power your sensors. Then energy efficiency will become an issue. And obviously environmental condition. If you're putting it in North Sea, probably it's extreme cold, you have to make sure your sensors also work under those conditions. If you put in a marine like under the sea, the sensors itself, the protection, the lifetime of the sensors become important. What type of in-network processes you will use here? You can aggregate data, for example. You can send an average of your monitoring the temperature. You can make the nodes to work together. If one of them detects a leak, you can ask the other nodes in the proximity. They can tell you the proximity of the leak, where it is. You can use different information between in-node collaboration and also aggregating data periodically to sending the information. Some simple data aggregation methods. That's it for today. Any questions? There is a lab, but there is no assignment or there is no practice for today's lab. Mainly we will be in the lab to